It is about an interesting function called the Raffle Function, but that's not a formal name. That's just a placeholder. In the end, we will discover that we probably have seen this function in other places. But in order to answer this question, just like mathematicians always do, most of the time do, they build a whole world around it. They solve a larger problem and they use their insight to go back and solve the original problem. Okay, so imagine you're participating in a raffle, infinite one. So there are infinitely many tickets. And on each ticket, there is a natural number. What's a natural number? A positive integer, 1, 2, 3, 4, and so on. Each of those tickets has one such number written on it. But there is a rule. For any number, let's say 10, the number of divisors of 10, if I put all of their tickets together and count them, that will be exactly 10. I take 6, the divisors of 6, put all of their tickets together, count them, is going to be 6. So let me demonstrate. So what are the divisors of 6? They are 1, 2, 3, and 6 itself. And so let's say, just hypothetically, the number 1 is written on 2 tickets. All right?
It's written on 2 tickets?
On 2, let's say. I don't know. I'm just like hypothesizing. The number 2 may be written on 3 tickets. The number 3 may be written on 1, and the number 6, well, there is nothing left for it because take a look, 2 plus 3 plus 1 is already 6. But maybe 1 is written only on 1, 2 is written on 2, 3 is written on 2, and maybe 6 then will have a 1. I just don't know ahead of time. But if I add up all of those tickets on which the numbers 1, 2, 3, and 6 are written, I'm going to get exactly 6 tickets, and on no other tickets those numbers are written. It's a very complicated rule. Let's take another number. For instance, 4. 4 is slightly simpler, or so it looks. The divisors are 1, 2, and 4, right? Okay. So those 3 numbers are written on some tickets. If I put them together, I should get a total of 4 tickets. So for instance, 1 could be written on 1, 2 on 1, and then for 4, I have to have 2, right?
I think I understand now. All right.
Yeah. So for every number, when I say number, I mean natural number. If I add up all of those tickets on which its divisors are written, I exactly have to equal to that. Okay, Brady. So let's say you go into this raffle and you have a favorite number. Give me your favorite 2-digit number.
I like the number 42.
Okay, for an obvious reason. 42, you are asking, would there be a ticket on which the number 42 is written? How many? Right? So that's what we want to find out.
Does every number have to be represented in the bucket of tickets, or can some numbers not have a ticket?
That is exactly my question.
Oh, okay.
To you.
Okay, right.
You give me a number, would that number be there?
Okay.
And how many of those numbers, how many tickets would have that number there? So 42, for example, as I said, is 2 times 3 times 7, right? How many divisors does 42 have? And this brings me to a relative...
Are you not counting 1 and 42?
Oh, I'm counting all. All I did here is I split 42 into its so-called prime power factorization. Okay. So it is 2 to the first times 3 to the first times 7 to the first. Okay, there will be exactly 8 divisors. 1, 2, 3, 7, those will be the prime divisors, but then I can start multiplying them. 6, 21, 14, and finally 42 itself. 8 divisors. If I add up the tickets on which all of these 8 numbers are written, I'm going to get exactly 42 tickets, but I don't know if 42 is actually written anywhere. Doesn't have to be. So we root for Brady. We want 42 to be written somewhere. Okay, so let us start now with this big construction process where we will construct a new world around the situation. So for starters, we need a placeholder, an anchor rather, for our unknown Raffle function. So we're going to call it R for Raffle. And if I put a number n there, that would mean the number of tickets with that n written on them. For instance, we are looking for Brady's R of 42. We want to know on how many tickets 42 is written. Could be 0.
Because, of course, 42 is a divisor of other numbers as well.
Yeah, and so it's a very intricate rule here. And is it actually possible even for it to happen? Or is this kind of a fake rule that just wishful thinking? Okay, so with this in mind, if you don't know any theory, you will start from simple numbers and figure out what's going on. So what's the simplest number here?
1.
1, that's right. So is 1 written on anything? Well, 1 is the only divisor of itself. So by this rule, 1 better be written on 1 ticket. So that's it. 1 is written on 1 ticket, and we have found our first value of our function. Keep on going now. 2. 2 has divisors, 1 and 2. So R of 1, the number of tickets for 1 plus R of 2, this better be 2. But 1 is already written on 1 ticket, so what's left for 2? 1. So both 1 and 2 are written on exactly 1 ticket.
And no more, they're done.
No more, no, that's it. And now we can use this in order to try to figure out what's happening for the other numbers. 3, on the other hand, let's see. Since it's a prime number, it has only these 2 divisors. And so when I do its condition, adding up the number of tickets, and I get 3, if this guy is 1, oh, I'm going to have 2 tickets on which 3 is written.
Because, oh yeah, okay, because there are 2 divisors.
That's right,
yeah, okay.
That's right. So if you want to draw a picture of this, 1 is written on 1 ticket, 2 is written on 1 ticket, but 3 is written on 2 tickets. Aha. Now, how about 4? We will still go just for a little bit to explore. Oh, we actually have for 4 the numbers. There they are, 1, 2, 4. Now, 1 was written on 1 ticket, 2 on 1. How much is left for 4? Have to add up to 4. So 4 will also be written on 2 tickets.
Oh, yeah, that's right. It has to add up to the number, not the number of divisors.
No.
Yes, yes.
So 4 is also written on 2 tickets. We're kind of thinking this is messy. Let us see if we can figure out 5 without much hassle. 1 would be written on 1 ticket. But overall I need 5. So what's left for 5? 4 tickets. 5 is very prodigious. Prodigious? Is that how you say it?
That's a word, yeah.
Yeah, prodigious. Yeah, it has lots of tickets on it. Here we start thinking, hold on, what's going to happen for 7? The prime numbers have only themselves and 1 as a divisor. But since 1 is already written on 1 ticket, what's left for them? Themselves minus 1. Oh, we have a formula. So something's cooking here. The raffle of a prime number, p, better be p minus 1. Yes, so now unfortunately for Brady's number 42, it's not prime, so I cannot yet determine what's happening. But 4 wasn't prime either, and we managed to do it. Are we ready now to find where 6, or how many tickets 6 will be written? Absolutely. We even have the demonstration pieces here. 1 is written on 1, 2 on 1, 3 on 2, 1 plus 1 plus 2, that's 4. There are 2 left for 6 to add up overall to 6. So R of 6 is 2. We know that R of 7, hold on, is 6, 1 less than 7, because that was prime. How about 8? 8 is complicated. It has a lot of powers of 2, right? But that's all, actually, not so complicated. 1 was written on 1, 2 on 1, that's 4. 4 was written on 2 tickets. We are keeping tab on this. And so how much is left for 8? 1 plus 1 plus 2, that's 4. For 8 overall, I need a 4.
It's kind of confusing that you used the prime divisors there and not just the divisors, but...
No. Actually, there is a reason for that.
Okay.
And you can see that the number of tickets on which each of those is written is going down by a power of 2. So it looks like R of 8 is 2 squared, which is 4. Okay, this is a lot of data. Maybe we start seeing patterns, maybe we don't. But if we soon don't see something, this is going to get overwhelming and we may drop it. No, we're not going to drop it. So let's have another piece of paper. Okay, we need a brilliant idea, an epiphany. And I'm going to go back to the number 6. Because for 6, we found the number of tickets on which it was written was 2. That's what was left over from the other numbers. Now, what was R of 2 and R of 3? Because 6 is equal to 2 times 3. I somehow want to relate the bigger output here to the smaller ones from before. Well, because 2 and 3 are prime, I'm just going to go one lower. And if I multiply them, I'm getting 2. So I am seeing a larger thing that might be happening on a larger scale. Aha, the function split along multiplication, right? That's interesting. That's interesting. Let's test this theory on 10, the number 10. Why on the number 10? Because 10 is like 6, even though it may not look like it. 10 is a product of 2 different primes. Okay, is that going to be equal to the product of the function on those 2 primes? Let's see. Well, R of 2 is 1 less than 2. R of 5 is 4. So overall, this is 4. Is R of 10 written on exactly 4 tickets? Well, that's easy to figure out because the divisors of 10 are 1, 2, 5, and 10 itself. 1 is written on 1, 2 is written on 1 ticket, 5 is written on 4, and what is 10 going to be written on? Remember that this whole thing has to add up to 10. 6 on 4 tickets, hey, that's our 4. Looks like we have come up upon another rule which we are not yet seeing why it works. But if I have 2 different prime numbers, P and Q, then the function breaks into a product of the corresponding values. Now, how would you prove that? Like you're asking a middle schooler, right? Well, maybe the middle schooler is going to run through exactly this same argument, but with letters, and will succeed because the divisors of this number are 1, P, Q, and PQ, right? So you're going to say this is on 1 ticket, this is on P minus 1, Q minus 1. How much is left for the whole thing to equal to PQ? Right, okay. Well, the ones are going to cancel, those 2. And then these I can put to the other side, so the question mark becomes PQ minus P minus Q plus this 1. You look at this like, does this factor? This has to factor. What is the factor? Well, PQ minus 1 multiply through. This is working. This is factoring, and P minus 1 was R of P, and Q minus 1 was R of. This is working. We proved this formula. I'm seeing something, but I'm not quite there yet. How about powers of a particular prime? Because here we had different primes coexisting, but what if I keep on feeding the same prime over and over again? We actually already saw a pattern of this with the 2's, didn't we? So for 2, we got 1 ticket. For 4, we got 2. For 8, we got 4. I mean, the pattern is kind of obvious, so what's happening? Let us do a crazy example, a general one. R of P to the 5. Okay, so what is this going to be equal to? P to the 5 has what divisors? 1, P, the powers of P, right? P squared, P cubed, P to the 4th, and P to the 5th. All of this has to add up to P to the 5th. Okay, so 1 goes on 1 ticket. P already we know is a prime to P minus 1. Then I'm going to ask you, what does P squared go into? Up to here, I have to add up to P squared. Okay, well, the ones are going to cancel if I add. So what should I add to P to get to P squared? P squared minus P. All right, now if I add up all of those, I have to get to P cubed. Well, the P's here conveniently cancel, so what should I add to P squared to get to P cubed? P cubed minus P squared. Aha, and if I go up to here to P to the 4th, those will cancel if I add up. I'm going to get these many tickets. And so on and so forth, we see P to the 5th minus P to the 4th. So it's the number minus the previous power. So we are now conjecturing with this argument, and if someone wants to prove it, you can do it by induction on the power, that the Raffle at P to the n is P to the n minus the previous power. This is as far as I'm going to go with messing with examples and looking for patterns. I promised the bigger picture, but I lied. I haven't yet given it to you. I have to give you a definition of a type of functions that I expect this Raffle function will turn into. So for that, I need a different sheet of paper. So for Brady's number 42, which was a product of 3 distinct primes, the situation is going to get complicated. Now, I can brute force it and show what's going to happen, but we want to solve this problem for all numbers. And therefore, we will introduce definition of a new type of functions. So f will be our function. First of all, I'm going to define what I'm going to call arithmetic functions. So it goes, let's just be simple here. Let's start from the natural numbers and go to the real numbers, but you can put complex numbers here, you can put whatever numbers. So we are going to call these functions, for which the inputs are natural numbers and the outputs are whatever, just simply arithmetic functions. And we will denote the set of arithmetic functions by A. Our Raffle function is an arithmetic function because in it we keep inputting natural numbers. So it is of this type. It's a very general type. Now, a more special type would be the set of so-called multiplicative functions. So, if in addition to being arithmetic, f satisfies the following property, f of a times b is equal to f of a times f of b, but I'm not yet done, for all a and b co-prime. What does it mean, co-prime? Relatively prime. They don't share any divisor other than 1. So for any such co-prime or relatively prime numbers, this has to happen.
So they do share? No.
They share just 1.
They share just 1.
Just 1. Okay? And so we will call those functions multiplicative because they split these products into some other products. They work well with multiplication.
Can you give me an example of 2 co-prime numbers, just so I've got it in my head?
Oh, absolutely.
Yeah.
Let's say 6, the other number shouldn't be even and it should not be divisible by 3. So how about 25? There you go. Those two numbers don't share a common divisor other than 1. So they are co-prime. And if f were multiplicative, then f has to split, what is this, 150? F of 150 should be f of 6 times f of 25. And it must work on the splitting principle as soon as you feed into it two prime, not two prime, but two co-prime numbers.
Okay.
So our Raffle function exhibits the signs of being multiplicative. For instance, for two distinct prime numbers, p and q, it has to do this, and it does it, because what was the Raffle of a prime number? It was p minus 1, right? The Raffle for the q would be q minus 1. Right? But when you multiply them on the previous sheet, we showed that this is indeed the Raffle of PQ. So our Raffle function looks like it should be multiplicative. Now I have to point out this condition here of being co-prime is super important, because if the two numbers are not relatively prime, this doesn't have to hold. And our Raffle function is doing exactly that. It's defying this rule for, let's say, the number 4. Because the number 4 is equal to 2 times 2. But is that equal to the Raffle of 2 times the Raffle of 2? No. Raffle of 2 is 1. So on the right-hand side, I just have 1. But Raffle of 4 wasn't 1. It was 2. So if they are not co-prime, don't even dare plug them into this formula. There are no guarantees that this formula would work. In fact, if it did work for any two natural numbers, there's going to be a special multiplicative function, which only I probably in this world call strongly multiplicative. And that would be yet a third set here of strongly multiplicative functions. So functions for which this rule f of ab is f of a times f of b works for all, the symbol for all natural numbers a and b. Okay, so let's step back and think about it. Our Raffle function, where do we expect it to be? By the way, this is like AMS, American Math Society, just for a fun mnemonic device. The Raffle function is obviously not strongly multiplicative because it already defies the rule for 4 here. But we hope, very much hope, that it will be multiplicative, so I'm going to put it right here with a question mark.
Haven't you already shown me here that it's strongly multiplicative?
But
what have you not shown me?
How about this? So numbers don't have to be just products of p and q. Or maybe they could be product of 3 distinct prime numbers, like 42. We haven't shown that this is working, right? For any prime power decomposition, just for some simple ones. Okay, now that we have this picture AMS, let's start putting familiar functions around. Let us get the feel of this multiplicative world. What function is also multiplicative? That, or maybe I will need another sheet of paper just for those functions.
Get you that?
Yeah. More functions, more Greek letters. Tau. Tau of n will simply be the number of divisors of n. That's an arithmetic function because all I'm plugging into it are just natural numbers and spitting out the number of divisors of n. Sigma of n. How about the sum of divisors of n? So these two functions turn out to be multiplicative, and you can try at home to prove it. Actually, it is more of a combinatorial problem here than number theory. They are multiplicative, and I'll give you just a couple of examples. So these are multiplicative functions. For instance,
So they're not just arithmetic. They're
exactly. Let's
they're in that
this.
second ring of the onion.
Yeah, right here. So, For instance, I mentioned this before. What is tau of 42? How many divisors does 42 have? Well, you split 42 into 2 times 3 times 7, and well, since I told you it's multiplicative, but you have to check this, it will split along this product, since all of those numbers here are co-prime to each other. And how many divisors does a prime number have? Well, 2. So each of those guys will be 2, 2, 2, so you're going to get our 8 from earlier discussion. So this tau is indeed multiplicative. I'm not proving it, that's your homework. So in fact, a famous formula for tau, and which is very useful in practice, is the following. Split n into its prime powers, like that. So these are distinct primes raised to some power. Okay? And then using the splitting principle for multiplicative functions, you will split it along those prime powers because they share nothing in common, no divisors. But you can directly count how many divisors does a prime power have. Well, you start from 1 and you'll build up to the full prime power. How many is that? Don't be fooled. It's not A1, it's A1 plus 1, not to forget the 1. So the whole practical formula that I was talking about is simply add 1 to all of those exponents and multiply. In fact, that's exactly what we did to 42 because the exponents were 1s. We just added 1 to them, we got 2, 2, 2, and that's your 8. Sigma is also multiplicative. So if I attempt to find the sum of the divisors of 42, instead of doing this crazy thing of listing them and adding them up, I'm just going to split it into much simpler, smaller problems like that, and then do it separately. Well, every prime number has only 2 divisors, 1 plus itself, so I'm just going to do that. Adding up the divisors, you're going to get what? 3 times 4 times 8, and feel free to finish off the computation. So both of those are just some everyday functions that you will find out they're multiplicative. But none of them are strongly multiplicative. Well, how do you prove that? I just need one counterexample. Where is the first counterexample we can look? 2 small numbers that are not relatively prime. What are those 2 first small numbers that share something other than 1? 2 and 2?
It's the same number.
Same number, yeah, 4. If I multiply them, I get 4. So if I attempt to find tau of 4, as we see, is this going to be equal to tau of 2 times tau of 2? Well, let's see. How many divisors does 2 have? Well, 1 in itself. This one, 1 in itself. But how many divisors does 4 have? Is it 4? No. 4 has 1, 2, 4. It has 3 divisors. Bingo. Tau is not strongly multiplicative. And you can check for sigma. Sigma of 4 is 1 plus 2 plus 4. I added all divisors, that's 7. And that spells trouble because 7 is definitely not sigma of 2, sigma of 2. In other words, add up the divisors of 2, that's 3, that's 3. Did I do this right? Whoops, 3 squared, 9. Those 2 are not equal. So in our picture, this AMS picture, definitely those 2 are not going to go inside, and the Raffle is also doing the same thing on 4. So if you want to show that something not strongly multiplicative, check first what it is doing at 4, and most likely it's not going to do that, but no guarantees. I do want to know at least a couple of strongly multiplicative functions. And the simplest ones that you can ever think in terms of functions are the constant functions. So are all constant functions multiplicative or strongly multiplicative? multiplicative? What is going on? It turns out that there are only two constant functions that are multiplicative and happen to be also strongly multiplicative. Very simple functions. The 0 function and the 1 function, which we are going to give another name, iota. That's not like I. Those two functions you can easily check. They're multiplicative and strongly multiplicative. Whatever you feed into them, they're always going to give you 0 or 1. But no other constant function even dares to be multiplicative. Let's take, for example, the constant function phi. G of n is going to be always 5, okay? So let us try, is this multiplicative? Well, g of 6 is supposed to then equal to g of 2 times g of 3. But how can this be possible? Every time I plug in something into my function, I output 5. So 5 is not equal to 5 times 5. So any number other than 0 and 1 is not going to work. Those constant other functions better be outside here. But 0 and 1 are always going to work because 0 is equal to 0 times 0 and 1 is equal to 1 times 1. You can see very easily there is no other one. So, okay, this is good. What else do we want? We want an operation on those functions. So we are getting higher in the structural level. So far we were looking at functions separately, but how do they communicate with each other? Let's get another sheet of paper.
All right.
Okay, operations on functions. So in elementary school, maybe middle school, what did you do to functions if you ever knew there were functions? You added them, you multiplied them, you subtracted them, right? Let's talk about multiplication because we're talking about multiplicative functions. What is this operation of multiplication on functions doing? So I'm going to do two tables here. One of them will be our new correct one, and the other one is the old, not quite useful. So multiplication for the old way of multiplying functions. So if I have a function f and I multiply it by the 0 function, how do you multiply two functions? So what is f g of n? All you're gonna do is just multiply their values, right? So if one of the functions is the 0 function, this is definitely gonna be 0 all the time. So I'm just gonna get the 0 function here, no wonders. If I multiply by the 1 function, so this guy will always be 1, so I'm gonna get back my original function f. As I was saying, this is not quite the right operation for us because it is not gonna give us our Raffle function back. There is one extra player that I want to define another function. That function I'm going to call the epsilon function. And the name is good for a reason coming from another area of mathematics, let's say calculus. There you talk about these limits and epsilon, delta. So epsilon there usually denotes a small positive number. Well, here I can't have 0.3 because that's not a natural number. But what would be the embodiment of this epsilon as a function in our world? It's kind of the smallest thing that's not 0, but it's still there. So what would that be? Epsilon of n would be 1 if n is 1, and then 0 if n is bigger. So what does this function do? It goes blip, and then it's dead. So that's the closest. So you're thinking, how useful could this function possibly be, right? So you've got 1 here, and then it's kind of dead for 2, 3, 4, and so on. Well, guess what? This epsilon function is also multiplicative. As a matter of fact, it's strongly multiplicative. So you can check that the epsilon function, I'm pulling my sheet here, this blip of a function is actually strongly multiplicative. We can check the rule for it. Is this epsilon of a b going to be equal to epsilon of a times epsilon of b for any two numbers a and b? Well, there are only two options for this epsilon to be 1 or 0. And it's going to be 1 only if whatever you feed into it is 1. So if any one of those a or b is bigger than 1, let's say b is 3, both sides are going to immediately die. They're going to be 0 because epsilon of something bigger than 1 is 0, and I'm going to get a 0 here. So what's left? Both of the numbers must be 1s. But then both sides will obviously be equal to 1. So there isn't much to check here, just kind of a logical argument. So what happens if I multiply by epsilon in my usual world of functions? Okay, so what happens? F of n times epsilon of n. Well, this is gonna die if n is bigger than 1, because epsilon is going to kill it. But if n is 1, there's going to be 1, and then just I'm going to get f of 1. So it's another blip function. At 1, you just get f of 1, and then you are dead. It's not a very interesting situation here. I'm just going to write it like this. Okay, what is the real operation? Not the real, but the new real operation. It's called Dirichlet product or Dirichlet convolution. Sounds very intimidating, but don't be so intimidated. I'm just going to use a star here to denote it, to look different from this dot. Okay, so we will have our usual players. So what is this operation? Here we go, the main definition. If I have two arithmetic functions, f and g, and I want to Dirichlet product them, multiply them. Okay, so what is this equal to? So what I'm going to do is take all of the divisors of n and start feeding them into the functions and adding up the result. So I'm going to have f of g1 times g of the opposite divisor, which will be n over d1. That will also be a divisor of n. And then I'm going to keep feeding another divisor into the first function and the opposite divisor into g. Keep on going until I exhaust all of the divisors, and that will be a new function that we are calling this Dirichlet convolution. Okay, let us take an example here. What happens if I do f star g of 6? Well, I mean, what are the divisors of 6? I'm going to feed 1 into f, but then I have to feed its opposite 6 into g. So those two multiply to 6. Then we do f of 2, g of 3, because those multiply to 6, and f of 3, g of 2, and finally f of 6, g of 1. Okay, we get the drift. If you want to scare ourselves, we can write a shortcut formula using summation, right? So what are we doing? We are feeding a divisor into f, and then we are feeding the opposite divisor into d, as long as d is a divisor of n. Or if you want a more kind of symmetric description, feed two divisors of n into f and g, d1 and d2, as long as they multiply to n. That's exactly the same definition. All right, so where does this lead us? This looks pretty artificial. Like, why did Dirichlet supposedly introduce it? Because it does what we want eventually. Let us see what would happen if I take f star 0. Well, f star 0, the 0 function is going to just kill everything, so it is still 0, same thing as before. But what happens if I star f with the 1 or iota function? I'm going to get something else. F star the iota function, or the 1 of n. Now remember that this will always give me 1, so I can just disregard the second part, the g's here. So I will end up simply adding the values of f on all of the divisors of n. Does this sound familiar? Adding up something about divisors of n. that was kind of like the sigma function that we talked about earlier, but in a bigger generality. So this is very important. I am going to write it as f of d as long as d is a divisor of n. And I'm going to give it another name. This is the sum function of f, and the notation will be s sub f. So what we were talking about here is actually a new function. For every function f, I create a new sum function. I said that I've seen this before. This reminds me earlier. So let us go back and check if we will recognize things. So we have divisors of n, this tau. What would happen if I take the sum function of just the constant one function? What is this? I'm supposed, for every divisor of n, I'm supposed to keep adding what this iota function is going to do to it. But this iota function, all it does is it spits out 1. So this is just ones, right? So how many ones did I add? As many divisors as I have. So this is the number of divisors of n, but we have a word for it. It is tau of n. So the sum function of the one function is tau. We are seeing connections. So these two functions from now on are somehow related in the same family. Let me talk about another function. Oh, they have a sheet of paper here. Identity. What is the identity function? So if you have studied like pre-calculus or maybe even some algebra, yeah? One of the simplest functions is f of x equals to x. So what does it do? For any input, it spits out the same thing. So it returns the identity of the input. That is what mathematicians call the identity function. So in this case, the identity function is going to take only natural inputs, but all it's going to do is going to spit them out as natural numbers, same natural number. So where is this identity function in our multiplicative land? Let us see. I think the identity function is going to be strongly multiplicative because identity of AB, well, that's supposed to be AB. Is that equal to the identity of A times identity of B? Well, certainly, that's A, that's B. You can't find anything much more strongly multiplicative than the identity function. Okay, what is the sum function of the identity function? What am I supposed to do? I have to take all divisors of n and feed them into the identity function and add up. So identity of d1 plus identity of d2, etc., for all of those divisors. Yeah, but the identity returns just the divisor. Isn't that the function that we talked about? That's the sum of the divisors, sigma. So our character functions are starting to pop up and get connected to each other. So now I need a new sheet of paper so we can draw chains of functions. So now chains of functions. We see that the functions are starting to get related to each other. What have we found? Just to remind you, if you have a function and Dirichlet with this one constant function, you're going to get what we call the sum function of f. And what did we find? That if I take the zero function and take its sum function, well, nothing interesting is going to happen. You're going to get the zero function. But if you take the iota function, that is the one function, and take its sum is going to be our tau, the number of divisors. And you can keep on going, but this is going to get complicated on this side. I kind of want to backtrack and say what happened when we started with the identity function and took its sum function. That turned out to be sigma. A couple more such examples. How about if I take, oh, remember that epsilon guy? The one that goes blip and then dies, right? So what happens if I take its sum function? Well, let us think. If I have a number n and I want to plug it in here, I just have to take the divisors of n and keep plugging them into epsilon, but this thing is gonna die after I plug in 1. So there's gonna be 1 and then zeros altogether. So no matter what n I plug in here, overall I'm just gonna get 1. So the sum function of the epsilon is iota, the constant function. The sum function of iota is tau, so we are getting a chain of functions. So epsilon by this sum function goes to the constant function 1, which eventually goes to tau. All right, where is the Raffle function? We forgot about it. It is here, creeping on us. What happens if I take the sum function of the Raffle function? And you're like, oh, the Raffle function is already complicated, and now you're asking me to take the sum function. Am I asking you to complicate or to simplify the situation? So let us think. Let's take it slow. So what's the sum function of the Raffle function at 6? All right, I have to keep taking the divisors of 6, feeding them into the Raffle function and adding up. So Raffle of 1 plus Raffle of 2 plus Raffle of 3 plus Raffle of 6. Hold on, haven't we seen this before? So what this means is that I am adding up how many tickets have the divisors of 6 written on them. How much was that? That was exactly 6. That's how the Raffle function was defined to start with. So this is supposed to be 6. I don't even have to write this. I plug in 6, I have to output 6. I plug in n, I have to output n, because this is really what the definition of the Raffle function was. The sum of the number of tickets on which divisors of n is written is n. But which function, when you plug into it n, outputs n? That's the identity function. So we have another chain of functions. The Raffle function was really defined in a very bizarre way, implicit way, so that its sum is the identity function. And then if I take the sum of the identity function, we already saw this earlier, that's the sigma function, the sum of the divisors of a number. Okay, so we have some handle on our Raffle function. Its sum function is the identity. So the question is, can I go back? If you give me the sum function of something, can I find the original function? Because that will be our Raffle function. So we somehow have to invert which operation? It's not the ordinary multiplication, but the Dirichlet product, or the Dirichlet convolution. So let's do it. So we are back to our multiplication table, but the new one. So remember that our operation is the Dirichlet product. Multiplying by 0, I'm getting the 0 function. Multiplying by 1 or the iota function, we already saw that this will be the sum function of f. So that's a pretty important thing. But I want to get back to f. I want to multiply by something so that I would get f. Just like in our usual ordinary multiplication, the 0 function plays the role of the 0 number. You multiply by the 0 number, you're dead. You get 0. But if you multiply by 1, you get yourself back, right? So we are looking for what functions play the roles of 0 and 1. In our new setup, the 0 is obvious, it's the same 0, but the 1 function is not anymore the 1 in that setup. It turns out it is this epsilon dude, the blip function. Why? So if you Dirichlet a function with the epsilon, at n. So what is this? I have to start taking divisors of n and feeding them into f and epsilon, but epsilon is going to kill all of them except until if I plug in 1 there. So the only thing that will survive out of this is f of n times epsilon of 1. So this guy will be 1, so you're going to get f of n. Oh, that is my function. So if I Dirichlet f with the epsilon blip function, I'm going to get f back. So who plays the role of 1 in our new setup?
The blip.
The blip function, that's right. This is our 1. And it is important to understand these rules so that I know now how to invert function. For instance, going back to middle school, right? What is the inverse of 5? You're going to ask me, well, with respect to which operation, addition or multiplication? Let's do multiplication. So what's the inverse of 5? Brady, what do you think?
I don't know, like a fifth.
A fifth, 1/5. I don't like 1/5 because it involves division, but it is the correct thing. Why? Because if I multiply 5 and this 1/5 business, I get the number 1, which is the 1 in this setup. Okay? So, if I want to find an inverse, Dirichlet inverse of a function, it means that when I multiply that inverse with f, what should I get? I should get the blip function. So f inverse in this setup would be such a function that if I Dirichlet product with f, I'm going to get the epsilon. And why am I so interested in this? Mathematically speaking, of course we're interested. We want to know what the inverses are. But in our setup, I had information, very scarce information about the Raffle function. All I knew is that its sum function, as we just discovered, is the identity function. So I somehow want to invert the situation, but what was the sum function? The sum function meant I take my Raffle and Dirichlet with the iota function, right? So we have this equation here. The Dirichlet product of our Raffle function with the constant 1 function is identity function. We know those two functions very well. There's nothing complicated about them. A middle schooler would know both of the functions. But how do I find this Raffle? So let's go back to elementary school. Just to understand the ideas.
You went to a different elementary school than me, but...
well, okay. Suppose we are trying to solve an equation like this. X times 5 is equal to 7. So how am I going to find x? You're going to tell me divide by 5, and I'm going to say, hold on, I don't have division here. I just have multiplication. So how do I get rid of this 5 on the left? I will multiply both sides by the inverse of 5. So you may think this is silly what I'm doing because everyone knows it, but keep in mind that we are going to take those ideas 3 levels higher to our Raffle function, so we really need to understand them. So I'm multiplying by the inverse of 5 here. Then what I'm going to do is I will switch parentheses. Which property of multiplication for numbers allows me to switch parentheses? That is associativity. So keep that in mind because we need to have associativity for our Dirichlet product, or else this whole argument is going to go to pieces. And then on the right hand side, I'm going to have 7 times 5 inverse. Yes, I know this is 7/5, but just forget about that for now. Now this guy here is our promised 1, and when I multiply those, I get x. And then you're going to get your 7/5. So that's the idea. Can we replicate this on our Raffle function? Let's try. So what did we have? The Raffle function, Dirichlet with the 1 function, is the identity, right? I need to find the Dirichlet inverse of the 1 function. So how do I find that? Okay, so the last big stretch here is to find the Dirichlet inverse of the one constant function. All right, that's not the reciprocal or anything crazy like this. It's even more crazy. It's the Dirichlet inverse. Let's give it a name. I'm just gonna call it mu for Mobius, because apparently he introduced it. You can check on the history. So what do I want for this Mobius function to do? I want it, when I Dirichlet it with the one function, to get, but that's the wrong one, to get our blip function, because it's the blip function that plays the role of one in our new world. Okay, we're gonna do a little bit of reverse engineering and I'll give you the formula. The formula is not so bad. But if I give it to you in the beginning, it will just seem very artificial. So just like for the Raffle function, we're going to do something similar. When I take the Dirichlet product with the iota function, that's actually simplified to the sum function of mu. So we are really trying to find which function has some function, the blip function. What does this mean? Starting from 1, if I plug in 1 on both sides, I should get 1, because that's what the blip function tells me. But what is this? This is just mu of 1. Okay, that's reasonable. Mu of 1 is 1, and that's actually what most multiplicative functions do anyway, so I'm fine. Let's try 2. So that should be epsilon of 2, but that's already dead. As a matter of fact, from now on, I have to be getting zeros. Okay, well, what's this? This is mu of 1 plus mu of 2, because these are the two divisors of 2. So overall, this should be 0. Hold on, but I know that mu of 1 is 1. How much is left for mu of 2? Negative 1, our first negative number. So some multiplicative functions output negative numbers. That's okay. So mu of 2 is negative 2. Not stopping.
-1?
Oh, negative 1. Sorry. I got carried away. How about mu of 3? Mu of 3. I'm going to carry the same absolute idea here. Epsilon of 3, that's 0. So mu of 1 plus mu of 3 is 0. This guy is 1. This better be negative 1. So what do you guys think now? Mu of anything else is going to be negative 1? No. No. Because see, what with this argument we can show is what happens to prime numbers. Because 2 and 3 were prime. They didn't have many divisors. So this has to be the blip of p, which is 0. On this side, we get mu of 1, mu of p must be 0. So what we showed is that mu of prime numbers is negative 1, not just mu of anything. So that's prime. But now you're going to say, hold on, how about 6? 6 is not prime. Okay, so what is mu of 6? All right, so we're just backtracking into, I still have to get 0 here. Mu of 1 plus mu of 2. You've seen me writing similar sums before, so this should become kind of automatic by now. Mu of 1 is 1. Oh, we just found those two. They are negative ones. How much is left for mu of 6 to compensate? 1. This is gonna get complicated. No, not so bad. So actually what this same argument shows is that if you have two different prime numbers like 2 and 3 and take their product, this is gonna be 1. And it makes perfect sense because I'm expecting it to be the product of those two guys, and this was negative 1, negative. All right, this is working. Okay, one more example, and then I'll give you the formula for homework. How about a 4, right? So mu of 4. All right, that should be dead. What are the divisors of 4? 1, 2, 4, right? This should be 0. This guy is 1. This guy is negative 1. How much is left for mu of 4? It's dead. It's 0. What do you think will mu of 8 be? If I were doing this with 8, all I had to do is add another mu of 8. but there is nothing for it left. It still has to be 0. What kind of a function is this? Okay, definition of the Mobius function, the Dirichlet inverse of the iota function. So, Mobius of n attains really only 3 values. So it's not anymore the blip function. It's kind of blippy up and down.
Double blip.
Double blip. 1, 0, and here I'm going to be dubious. It's either 1 or minus 1. So it will be 1 when n is 1. It will be negative 1 to the k depending on how many prime divisors distinct it has. But it cannot have the square of any prime divisor. So n has to be literally just a product of k distinct primes, period. 8 and 4 were bad because they had the same prime raised to a higher power. 2 squared was dividing them. So these numbers here are called San Francisco primes. No, I'm just kidding. Square free numbers. There is no square that divides them except for 1. That's it. Okay, 0 if n is not a San Francisco number. It's not square free number. So in other words, if some prime squared divides n, is a divisor, then we're just gonna die. Now, this is for homework. It's a great exercise. Try it out. And mu, what kind of a function would mu be? Where is my diagram? Mu is going to be also just multiplicative, not strongly multiplicative. You know that because mu of 4, if it was strongly multiplicative, it would have to split like this, but those guys are a -1, while this one is dead. It's not going to work. So it's not strongly multiplicative, but that's okay. Multiplicative is really our land here. Okay, now let's finish the story. Why do they need the Mobius function to start with? Because we wanted to invert the one function. Why did they want to invert the one function? Going back to the Raffle function. So the sum function of the Raffle function is the identity. This was the original convoluted, weird, in disguise definition of the Raffle function. Okay, but we know what sum function is. It becomes or can be encoded as the Dirichlet product of any function with the iota function. So that has to be the identity. Now, this becomes our equation, the equation for x that we are trying to find. So I'm trying to solve for this Raffle. Okay, what properties does the Dirichlet product have? I'm going to list them for you. And luckily, they correspond to what you used from elementary school about multiplication. So the Dirichlet product is everything you want it to be. It is commutative. So if you have f Dirichlet g, you can flip-flop those, no problem. It acts like a regular multiplication. It is also associative. If you have 3 functions and bother to take the Dirichlet product, you can move parentheses freely around, and you can therefore write triple products. Doesn't matter which ones you multiply first, and you can swap them around. That's for homework. A little bit boring, but nothing too complicated. So with this in mind, we just found that the inverse of the one function was our new player, Mobius. Okay, am I ready to get rid of this? Absolutely. So, the nitty-gritty, is that the expression? Details here go like this. Multiply both sides, Dirichlet multiply them by mu. I can put mu wherever I want, on the left or on the right. Then change the parentheses. Okay. So that's still this. Then this guy, because they are inverses of each other, will be the blip function epsilon, which plays the role of 1. But what happens when I Dirichlet with the epsilon function? It plays the role of 1. I'm going to get my original function. So from here, we draw the conclusion that the Raffle function is the Mobius function Dirichlet with the identity function. And in fact, this is a special example of something called the Mobius inversion formula, because it uses the Mobius function. Okay, but what is this good for? It is a direct formula for the Raffle function, but I don't care about the exact formula. I care that it exists. Why? Because multiplicativity is contagious. So that's another theorem that you may prove on the side, and it says the following. If two functions f and g are multiplicative, so they are in somewhere here, they could be even strongly multiplicative. If I take their Dirichlet product, that's going to be some function. Where do you think that Dirichlet product will be this new function? It will still be in multiplicative land. And that's power. If you know that a function is multiplicative, you can find what it is equal to, a direct formula to work with very easily, and I'll show you on the next and last sheet of paper.
All right.
So, right here what we see is the following. Identity is not just multiplicative, it's strongly multiplicative, but do I care about that? Do I seem to care? I don't. It's just multiplicative. Mu, as a homework I gave you here, is also multiplicative. Then the product of them will be multiplicative, which implies that our mysterious Raffle function is indeed in multiplicative land. Let's find what function that is. Fine. Okay, we start now with the huge advantage that the Raffle function is multiplicative. That gives us the possibility to split the Raffle function onto the prime powers immediately. So, if I feed to it any n, and I write the prime power decomposition of n, p1 to the a1, p2 to the a2, blah blah, pk to the ak, because those prime powers are pairwise co-prime, multiplicativity kicks in, and I can split this into the product of what the Raffle function is doing on prime powers. But guess what? We already had a formula like this from earlier. We found this when we were doing Raffle of 2, 4, 8, and we noticed it. So what's the formula for each of those prime powers? I'm going to write it here on the side, and then we'll use it. Take the full power and subtract from it the previous power. Okay, putting this together, I'm going to write each of those powers and subtract from it the previous power. This may look intimidating from the beginning, but hold your horses. It's still a direct formula, and we'll find perhaps even easier version of it. Okay, now you are going to be shocked when I tell you I'm going to simplify this formula not by factoring the smaller power, but by over-factoring the larger one. I mean, who in their right mind is doing that? Because I'm going to end up with fractions. Well, hold on. Hold your horses. P to the m, if I factor it, all I have from it left is 1. What am I left with here? Well, when I multiply those two, I should get p to the m minus 1. So I'm getting this fraction. Okay, just let's try it here. So I'm going to over-factor, and I'm just going to do this in the very beginning, put them together, all of those prime powers, the larger ones. What's left? From the first one, I just have 1 minus 1 over p1. From the second one, 1 minus 1 over p2. Keep on going, 1 minus 1 over pk. But what is this? This is my original number n, because I have all of its particles here. So I get the following very nice formula for the Raffle function. It is the original number n times 1 minus the reciprocal of its prime divisors, all multiplied. That's it. Some of you may already start recognizing this as a formula of another famous function called the Euler totient function. And it is. That is precisely equal from a different direction to that Euler function. So it turns out that our Raffle function was nothing more, nothing less than the Euler function. And the way it was given to us in disguise was the following. They basically told us that the sum function of the Euler function is the identity. And of course, in the beginning, we did not know any of this. But now we have the full power to work with this Raffle function. Now, before I show you some examples, what is the Euler function? The Euler function is defined in a way that looks like exactly the opposite to the Raffle function. What is the Euler function of n? It is the number of numbers, which means natural numbers, between 1 and n, possibly inclusive, that are co-prime with n. All right, what does this mean? Let's say phi of 5. Well, what numbers from 1 to 5 are relatively prime to 5? I mean, everything except for 5, because 5 is prime. So that would be 4. And of course, you recognize that that's 5 minus 1, which was our Raffle function of 5. That shouldn't be a surprise. Okay, what is phi of 6? All right, so what? From 1 to 6 are relatively prime to 6. Well, 2 is not, 3 is not, 6 is not, 4 is not. So just 1 and 5. So this should be 2. Is this what the Raffle function would have given us? Yeah. The Raffle function of 6, I can split it. I don't have to go all the way to this formula. I can just split it on Raffle of 2, Raffle of 3, because it's multiplicative. Raffle of 2, that's 2 minus 1, 1. Raffle of 3, that's 3 minus 1, 2. This is working. Okay? So, but it just gives me a headache. A mild headache. So the Raffle function is defined using just divisors of n. Something that truly can divide n. The Euler function is defined using relatively prime numbers to n. And then there is all of this array of other numbers, third-type numbers, that are neither divisors of n nor relatively prime to n. How come the Raffle function should be equal to the Euler function? Well, we have the proof, we saw it. You may try to find another proof, but I think we need to answer Brady's question about 42.
Yes.
So, Brady wants to find out if 42 would be written on any ticket, and if yes, on how many tickets, so he can get them for his friends. So let's go for it. Raffle of 42. This should be easy peasy now because we split into its prime power factorization, which happens to be products of primes. Let's do it two different ways because I know that the Raffle now is multiplicative. I can split it into a product of its values on those. These are primes. So I just lower them down by 1. 1, 2, 6, so it looks like it's 12. Let's try differently.
So there are 12 tickets with number 42 written on it.
Yeah. Let's look at this formula here. Would that formula also give us the same answer? So I would have to put the number 42 and then do some stupid things with these fractions. Okay, well, you know what? I am really lazy. I don't want to deal with those fractions. So I'm going to take 2 from here and multiply it by this whole factor. 3 from here multiply. And 7 from here multiply. And there will be nothing left out of 42. So when I multiply by 2, I'm going to get 2 minus 1. When I multiply by 3, 3 minus 1, 7 minus 1, and guess what? That is precisely what we got before. Shall we try one last example?
Okay.
What is your most preferred year? This year, 2024, last year, or next year?
I like this year.
This year,
Yeah.
okay. Turning around.
Do you want another piece? I've got one more piece.
You want another one? Okay.
There you go.
Let's do another one.
Show me 2024. Okay. Yeah.
2024. You want to know how many tickets have this number written on them. Okay, let's do it. What do I need to know about 2024?
Prime factorization.
Brady learns so fast. Now, what is it? I mean, it's divisible by 2. Is it divisible by 4? That 24 pretty much tells me. How about 8? Pretty much, I know because of that. So this is going to be 2 cubed. And when I divide by that, it's still going to be, So I'm going to reach for my calculator. Where's my calculator? There is my calculator. So let's do it. 2024 divided by 8. 253, is this prime?
It's prime-ish.
Prime-ish. Well, let's see. It's definitely not divisible by 2, not divisible by 3. Not divisible by 7. No, it's not divisible by 7. It's divisible by 11. Let's try by 11. Well, there was this nice criteria of plus minus the digits of a number. So 2 minus 5 plus 3, that's 0. That's divisible by 11. Let's try. Divide by 11. 23. And 23 is prime. So we are on a roll. So let's just split it because the raffle is multiplicative. Okay. The prime numbers are easy to deal with. I'll just lower them by 1. 11 becomes 10, 23 becomes 22. This guy, if you remember our formula, I will have to take the full power and subtract the previous power. So this will be, and I'm sure we found it like several times before. Okay, so what's that? 880 tickets. Have that. That's a prolific number. Yeah. And so Brady, you were worried at some point during this talk that some number may fail to be written. Do you think there is such a number?
I don't.
No, because look at this formula. This formula, first of all, it has to give you a natural number, no matter what. We know that those primes will be canceled after you multiply through. Can this be 0? No. There is no way this is 0. So the original way that this problem was given to me when I was training on the Bulgarian team for the International Math Olympiad was they gave us this convoluted description of the Raffle function, and they said, prove that every number is written on at least one ticket. But they didn't tell you how many. So you had to solve this larger problem of actually finding what the function is before you can answer this. But how do you find what the function is? You further enlarge the problem to the multiplicative land. Talk about properties there. The blip function, the Mobius function, Dirichlet inverses, Dirichlet products. And then put everything together and come back eventually. What did we use that for anyways? To show that the Raffle function is multiplicative. That's all I cared for. Once I knew this, we were home free. We can split everything on its building blocks, which are the prime powers, and we could kill the problem in no time.
So you did this during the Math Olympiad as a training for the Math Olympiad. Mm-hmm. How old were you?
Maybe 10th grade. Yeah. It's not that complicated. If take it piece by piece, and of course, if your elementary education in math is pretty strong.
Yeah. How come you haven't done this on Numberphile until now?
Well, you now know it is a technical subject. It involves a progression of many, many steps and enlarging the problem several times before you can solve the bigger issue, the bigger problem, and come back. So I just want you to try some simpler things before I graduate to this very complicated topic.
Okay. When I saw your notes there, I thought, oh, this is going to be quite a quick one. Wow, well, if you made it this far, I'm guessing you might like videos about really long proofs, and you might also enjoy videos with Zvezda here. So if you have a look at the links below, I've put playlists and links to more stuff just like this. More Zvezda videos, more long proofs. Knock yourself out.
The diameter of this, we can work out the diameter of this, and then we've got the radius. So how can we do that? This is epic.